Hi viewers, welcome to the last segment of the 6th lecture of this course of online series of lectures for Introduction to Category Theory. So we were with the concept of fiber sum of sets. Here the fiber sum of the set X and Y over the set W, and there were so in the last segment we discussed this idea of obtaining this fiber sum as a quotient set of the coproduct of these two sets X and Y. Okay, so now I will explain the two natural inclusions that arise in this context. Namely, I1 from X to the fiber sum of X and Y over W, and I2 the inclusion of Y in the fiber sum. Okay. They can naturally be included in the in this set. Okay. So now, if we define these two inclusions, then under this definition, the following diagram can use. You remember the pushout diagram that we discussed in the last segment? And then on this bottom right corner of this diagram, we'll have this fiber sum. And this is the inclusion I1 and this is the inclusion I2. And we put a corner symbol here to designate pushout. So let me define pushout now. Pushout is nothing but the same as the fiber sum. Okay. So this diagram can use. Okay. The X, the quotient space of the disjoint union of X and Y is called the pushout of X and Y over W. The corner symbol designates pushout. Okay. Alright. So I want to give you an example of pushout, although it's not written in the lecture notes. Let me try to simplify it for you. It's an example from the category of topological spaces denoted by TOP. This is the category of topological spaces where the objects are topological spaces and the corresponding morphisms are continuous functions between topological spaces. Okay. So here is one topological space, here is another topological space, and they are talking to each other via continuous functions. Okay. These are topological spaces, and they talk to each other by means of continuous functions. Okay, so these are the morphisms of this category, and these are the corresponding objects. Okay, so in the last lecture, I I discussed terminal object of a category. Okay. Okay. So there I told you that a terminal object is a distinguished object in the category denoted by 1 in the category C, so that for any other object in this category denoted by C, I have a unique morphism from X to 1. And if this terminal object exists in the category, that has to be unique up to unique isomorphism. Okay? So this is something that I discussed in the last lecture. So when we talk about the category of this topological space, and also I explained, and I gave an example of a terminal object, of the terminal object for the category of set, where the terminal objects were one-point sets or singletons, okay, like this. Right. For this topological space top, the terminal object is a one-point topological space. It means that it's a topological space whose underlying set is a singleton. Okay. And by the definition of terminal object, there has to be a unique morphism from any other topological space to itself. Okay, because this is the terminal object. So, if I take another topological space, which is a circle, then I have a unique morphism. And what is unique? What is morphism in this context? The morphism is a continuous function. So, if you have circle, then there is a unique continuous function from the circle to this one-point topological space. What is that? Everything is taken to that point. Everything on the circle is taken to that point. That is the continuous function. Okay? Okay. Good. Now, let us try to draw a diagram. Okay? So, on the top left corner of the diagram, I have a circle S1. Okay? And I don't know how to call this. So let us call this map C. So let us call this map C, which takes C is a continuous function by the argument of terminal object here. S1 is taken to a single point. Okay? In topological space, in the category of topological spaces. Now, I draw a 2-disk here. A 2-disk here. Okay. And I have the inclusion of this circle as the boundary of 2 disks here. This is also a continuous function. One can check. One requires basic topological idea to do that. So there is always a continuous function from this circle to this disk, which is realized as the boundary of this disk, and this is the continuous function. So these are two functions. Okay? So we can think about the pushout in this diagram, and in order to do that, I have to take the disjoint union of these two disks with this single point topological space and quotient it out by the underlying equivalence relation. Right? You remember that the equivalence relation was given by the following, right? For this general diagram, I'm not going to take the coproduct of x and y, okay, or the disjoint union of the two sets. I got to take the quotient of the disjoint union by some equivalence relation, and the relation was so if we take two pairs from here, one is fw comma 0. This 0 index means that we are with the pairs which correspond to this first element, the first constituent of this disjoint union, which is of course a set. And if we take GW comma 1, which corresponds to the second constituent of this disjoint union, and they have to be identified for all W in this set W. Okay? So if we identify such pairs in this disjoint union, the resulting set is precisely the quotient set that we have called as the pushout of x and y over W. Okay, so what is this thing for this example? Alright? So you see that under this map, so the FWs, so this is the map F. Okay? So what are FWs? Okay. So the images. So FW are the images of W for all W in W. So so the images of this circle under this map, who are this boundary? Is this boundary, okay? So all the images, if you take all the images under this map group, you will get the boundary of this two disk. And what will be the image of this continuous map C? As a single point, okay? And the equivalence relation tells you that you have to identify this boundary with this point. What does that mean? You have this two disks, and you have to wrap these two disks in such a way that the boundary becomes a single point, okay? That way it becomes a two-sphere. Football, right? So finally what you have here on this bottom right corner is a two-sphere. Okay? The north pole of this two-sphere is precisely this point. And it's the same, this point is also the same as the boundary, because this boundary has been, mapped. You have to wrap it in such a way that this boundary becomes a point. And that way, the end result is a two-sphere. This is S2, this is D2, a two-disk, and this is just a single point, one point topological space. This is the inclusion I1 that we have talked about earlier, and this is the inclusion I2 that we also had discussed earlier. Okay? Note one thing, that this inclusion takes, if you take any point from the interior of this two disk that precisely corresponds to a single point, a unique point, a single point in S2, but yeah. this North Pole, so that it's not an injective map. It's a many-to-one map. Okay? Although it's injective because this has been taken to this North Pole. Alright? So this S2 is the push out of D2 and this single point topological space over the circle S1 in this example. Alright? Good. So now I will discuss the universal property of pushout. I need to discuss the universal property of pushout. Universal property of pushout. Okay? So here is lemma 2. I'm not going to prove it. I'll leave it as an exercise for you. Okay? Lemma 2 with this thing, the same name, universal property of pushout. Okay? Suppose we have the following diagram of sets. The following diagram of sets and functions which we already discussed earlier, from W to Y and from W to X. Okay? So I just change the places of X and Y here. It doesn't matter. So I have 3 sets and 2 functions between the sets. Now for any set, right here, for any set A and commutative solid arrow diagram, as below. So which I draw first here. Let me draw the commutative solid arrow diagram here. From W we go to Y via U, and from W we go down to X via T, and what is in that right hand corner? The bottom corner, we have this push out of X and Y over W, and there is this inclusion I2 in this case, and this inclusion I1 here, and there is a corner symbol here designating that this is a push out, right? So this is for any set A here. So let me draw it first, and then I'm going to write something here. Bracket. Okay. This is G. This is F. Okay. And it tells you that a continuous continues after as below, okay, inside bracket. That is functions f from x to a and g from y to a, such that you see that you can go from W to A via this path or this path. They should be the same. They should result in the same thing. Which means that G composed with U, I should put a circle here. G composed with U should be equal to F composed with T. F composed with T. This is the solid arrow diagram that we have here. Okay? So if this is the situation, then there exists a unique arrow. So I'm denoting this unique arrow by this sign from this pushout to that set A. Drawing this unique arrow here. This is what we have denoted by this symbol. Right? So the universal property of pushout tells that there exists such a unique map for which everything commutes. So that making everything commute. Making everything commute. So if everything commutes, then we'll have if everything commutes, so take this triangle here. So if this triangle has to commute, okay, and if this triangle commutes, then this unit function that we want to exist, that composed with this inclusion map I1 has to be equal to, this path has to be the same as this path. This has to be equal to F. Okay? And this triangle has to commute as well, from which we see that we can go from Y to A in these two paths, and they have to result in the same thing at the end. And it tells you that this unique arrow composed with I2 has to be the same as G. Okay, so this is the statement of the universal property of pushout. I leave it as an exercise for you. Okay. Alright. So now we move into the discussion of coequalizer. Which goes parallel to what we studied in the last lecture called equalizer. Okay? It's a dual notion of what we call equalizer for the category of set. Okay, so the proof of the lemma, what was that? the proof of lemma 2 is left as an exercise. Please do the exercise. So coequalizer definition. Suppose we are given two parallel arrows. Suppose we are given two parallel arrows between x and y. Okay, one is denoted by f, the other denoted by g. The coequalizer of f and g appearing in the following commutative diagram these are the two parallel arrows between x and y, and that will go to coequalizer of f and g. If you remember what we did in the last lecture while discussing equalizer, that was here on this end. Now here on the other end, the coequalizer, which is a quotient set of y. So the coequalizer of f and g appearing in the following commutative diagram is defined as coequalizer f comma g is defined as the quotient space of y by the equivalence relation, where you identify fx and gx. Okay? So inside y, there are y is a set, and inside y are elements like fx, gx, and there are some elements which are neither fx nor gx. Okay? Whenever you find elements like one is fx, another is gx, you have to identify them. Okay? You have to make them the same. And under that equivalence relation, this y set becomes the coequalizer of f and g. I'll give you an example to understand it more clearly. So this is the definition of coequalizer. Let me give you an example of. Example. Okay. Consider the following two parallel arrows between from R to itself. Okay. So from R to here in this example, both x and y are R. There are two parallel arrows. There are parallel arrows which are denoted by f and g, where f of x equal to x and g of x is equal to x plus 1. I need to know what the coequalizer is. The coequalizer of these two functions. I need to know. if I try to draw the numerative diagram that I defined earlier, while I was defining the idea of coequalizer, there are R and two parallel arrows, F and G. So I'm trying to draw that numerative diagram, and from R there will be a quotient path. Okay. There will be a quotient path from R, quotiented out by some equivalence relation, and over that, what is that equivalence relation? Inside R, there is f of x and there is g of x. We need to identify it. And after the identification of f of x and g of x inside R, what we get at the end as a set is called this quotient set. And we will see that this is topologically equivalent to a circle. Okay? So let's take the example. Let's take the real line. Okay? So 0 is here, 1 is here, 2 is here, 3 is here, and to the left of 0 we have -1, we have -2, we have -3, and so forth, towards negative infinity. Okay? So, what are we doing? We are identifying x with x plus 1. Okay? One is f of x and the other one is g of x. So we are identifying these two images under f and g. Okay? Okay. So 0 is identified with 1. 1 is identified with 2. 2 is identified with 3, meaning that all the integers are identified and there is a single point representing all the integers in the real line here. Okay? Okay. So, if we choose any other point on the set of real lines which is not an integer that can be brought to this open closed interval from 0 to 1 by means of the given equivalence relation. Okay? And what is the equivalence relation? The equivalence relation is that x is identified with x plus 1. Okay? Alright. So let's take some examples. So if we choose, say, 0.43, no, say 2.43, and there is 1.43, which is one distance apart from 2.43, 1.43, and there is 0.43, okay, and so there is one to the left of 0, which is also equivalent to 0.43. Okay? Just have to subtract 1 from 0.43 to get that point here on the left side of 0. So these are all equivalent, meaning that they belong to the same equivalence class. So 2.43 can be brought to 0.43, which lies in this interval. Okay? So that way we can see that any number on the set of real lines under this equivalence relation can be brought into this interval. Okay? Meaning that every number on the set of real lines has a representative in this interval. Okay. So, but this does not tell the whole picture because you don't see the thing from here that 0 is identified with 1. And when you do that, this interval becomes circle. when you identify the endpoints of 0, 1, meaning that you have 0 and you have 1 here which is not included, you take these 2 points and you merge them, you end up with a circle. Okay? So it tells you that the equalizer of f and g, where f is given by x and g is given by x plus 1, is topologically equivalent to a circle. Okay? Alright. Now that we know what a coequalizer is, we move on to its universal property given by a proposition. Let me state the proposition first, and I will leave the proof of the proposition as an exercise for you. Okay? So here is the proposition. Proposition 1. Under the name of universal property of coequalizer. Okay. So let me draw the diagram first because it's easier if we have the diagram to state the proposition. So there are 2 parallel arrows between B and A, and under the quotient map, A goes to the coequalizer of f and g, and there is this set T, and there is a map from A to T called H. There exists a unit map from the coequalizer to T, which we denote by K, so that everything commutes. Alright? So this under the quotient map, so looks like this, okay? Which has been discussed in the previous segment while we were doing equivalence class and equivalence relation, and coequalizer of f and g is defined as A quotient out the equivalence relation. Okay, so here is the statement. Let BA be sets and FG are functions from B to A these functions, I need to change the marker. So the coequalizer denoted by 2f comma g with the quotient map Q from A to the coequalizer of f and g satisfies the following universal property. Following universal property. First one, Q composed with F should be the same as Q composed with J, because the entire diagram commutes. Q composed with F should be the same as Q composed with G. The second one. For every set T, and every map H from A to T, H from A to T, such that so you can go from B to T in these two paths. First go from B to A via F, and then from A to T via H. Or you can take another route. First go from B to A via G, and then go from A to T via H. The result should be the same, meaning that H composed with G should be the same as H composed with F. There exists a unique map. K from the coequalizer of F and G to T, such that the above diagram commutes, such that the above diagram commutes. Okay. That is, i.e., K composed with Q should be the same as H. K composed with Q should be the same as H. Okay. So this statement goes parallel to the statement of the universal property of equalizer. So go over the proof of the universal property of equalizer and try to imitate that proof in this context and prove this statement of this proposition. Okay, that is left as an exercise for you. Okay. Now we'll discuss finite colimit in the category of sets. As the last topic of the safe lecture. Okay. Finite colimit in the category of sets. Okay. All right. So I'm not sure if you remember what we did during the discussion of product, pullback, and equalizer. We saw that in all those cases we have a distinguished terminal object. Okay. And that terminal object belongs to some category that we did not discuss quite because we don't have enough background to understand all those things in the abstract setup. I vaguely told you that there was some category called Cool D for a diagram functor from an index category to a given category C. Okay? And the limit of that diagram functor is a terminal object in this category. Okay? So in this situation, we have a diagram functor again, a diagram functor from an index category to the given category C. We still have it, but instead of that category of cone D, we have a new category called cocone D. All right? And we're looking for a distinguished object, which in this case is an initial object in this category, which will be the co-limit of this diagram function. Okay? So instead of terminal object, we're looking for initial object in this category. So we were looking for a terminal object in that category, which was the limit of the diagram function, and now we're looking for an initial object in this category of cocone of D, where the initial object is the co-limit of this diagram function. Okay? So let me summarize all these things here. Co-limit. So the idea of co-limit in the abstract setup will be taken up in detail later in this course. So let me summarize what I have told you right now. One refers to the co-limit of the functor diagram from an index category to the given category C. All right. So in our context, the category is the category of sets, but we can do it for any abstract category. So the co-limit of the functor diagram so one refers to the co-limit of the functor diagram D from J to C as an initial object okay, in some category which I have stated here, in some category called cocone of D. Okay. So what is the definition of an initial object in a given category? So it means that it's a distinguished object in the category C, such that this is the initial object that we are denoting with 0. Okay? So for any other object in the category, there is a unique morphism from this initial object to the object X. And so this is the notion of initial object in a given category. Okay? So this means this idea of initial object in a category, using that notion of initial object in a category, we see that there is a unique morphism. There is a unique morphism from this distinguished object, which is this initial object that we are talking about. From this distinguished object of cocone D to any other cocone of D. All right. So this is the category, and in this category, the initial object is precisely the colimit of the diagram functor that we are considering. Okay. All right. So examples. Okay. All right. So now, when this index category is a finite category, we say that the underlying colimit is a finite colimit. Okay. So examples of finite colimits in the context of the category of set, meaning that when C is this category of sets, we have examples of finite colimits as coproduct, pushouts, and coequalizer. These are all examples of finite colimits in the context of the category of set. Okay, and they all are related to initial object of category of some category called co-cone D for different diagrams, for different diagram functors. No, meaning that by which we mean for different diagram functor, we mean that for these three cases, the index category will be different. Okay. So, all right, that was pretty much it. This is what we wanted to discuss in this sixth lecture. So, in the following lecture, we will discuss some other important category theoretic notions called epimorphism, monomorphism, and we'll also learn how to query in the category set. Okay? Using exponential objects. Okay? These things will be taken up in the next lecture. Okay? Thank you for attending these things will be taken up in the 7th lecture. So thank you for attending the 6th lecture. Bye.